Okay, that was a lot like the Oasis song by Oasis, where I cough first. So hello, welcome back again to one of my video log recording sessions where I talk about genetic genetic algorithms and things related to it, concepts, ideas, my mistakes, my terrible programming skills, etc. So, in my last video, was it the very last video? Well, in my last video where I talked about how I should go about, or how I would go about tracking evolution of individual entities, or evolution of entities on an individual basis. I mentioned that something like a learning function should be implemented for each individual entity, meaning that the entity that is given a chance, or that feels like it, in quotes, feels like learning from one or some of the top entities, should try to learn and mimic the genes of those of the entity or entities chosen. And I have done that, and today I'll be sharing some of the results or changes that has brought. So previously, well, I have implemented that feature. It was the function called learn from others. But what I wanted to know was what I wanted to know further and deeper, more about, was how the learn rate, not the learning rate in other machine learning concepts and techniques, but the learn rate in this case. I don't know if there's an official jargon for this, terminology for this. There should be, but I just coined it because I was too lazy to Google it. How the learn rate affects the outcomes outcomes for the entities as a collective group and as individuals. And in the previous video, the learn rate was 0.3. So naturally, you would think, what if the learn rate is something like 0.0, which is, absolutely no, 0. The entities don't learn. They try to learn, but they won't, because their ability to learn, which is the learn rate, is set to 0, so they cannot learn. Or what if the learn rate is 0.7, higher than 0.3? What if it's 1.0? So that's what I wanted to find out. So that's one thing. So I would have I would have the learn rate, which can range from 0.0 to 1.0, right? And then what I do have to set the other value, the other axis, in a way, or dimension, whatever, that I have to set is the range within the world, the range within the world per generation, within each generation, of entities that are entities that can learn, or that are given the chance to learn. So it could be the top 10% who can learn from themselves, or it could be let's try this. It could be the top 20%, any entities within here. It could be this 20%, or it could be this 40%, or it could be this 70%, or it could be the bottom 20%, or it could be the entire thing, 100% of the world. So I call this the learn rate. I think candidate, was it? Yeah, I actually call this the candidate range. Candidate, that's a bad N. Candidate range, and that's the learn rate. And then one final, but well, minor. It's not that it's not a big difference, and it turns out it wasn't that much of a difference. But anyway, range. And one more thing is whether I add the newborns first, and then have the entities within the candidate range learn, or if I have them learn first and add the newborns. So if you remember, the newborns are the entities born from the procreate function given a procreate method. But yeah, so these are the three differences, but this one I chose not to include within, or I chose not to vary within one Jupyter notebook. So I would just have it fixed to either add first or learn later, or learn first or add later, and then I would do a grid. I would perform a grid search with all of these variables changing. So if I want to illustrate that further. So if the starting decile is 0, meaning from 0%, and the end decile is of course 100, but it just says 1 there. And then from the starting decile of 0 and the end decile of 0, which is actually nothing, that's one possibility, that's one case, one outcome. And from 0 to 0.1, that's another one, that's 10%, the top 10%. From 0 to 0.2, that's top 20%. So all these mean nothing, but this, you just have to count the number of cells after this first column. Same here, after this first column. So there's only one orange cell, so that's 10%, the top 10% from 0 to 0.1, or yeah, from the top 0% to the top 10%. The next is from the top 0% to the top 20%, until 30%, until 40%, until 50%, until 60%, 70, 80, 90, 100. So if you were to speak in cumulative terms, this is the entire entire 100% of the world per generation. This is 90. This is 90, this is 80, this is 70, this is 60, this is 0, 0, 10, 20, 30, I'm so bad, 40, 50. And then when the starting decile is set to 0.1, as in from the top 10% until the next decile, the first one is 0. The second one is again another 10%, another 20. So it would go something like this. Let's just do this. 30, 40, 50, 60, 70, 80, 90. So it would go something like this. And then the same goes here. Yep. Just let me work. There we go. So this is how I intend to cover all learn rate dash candidate range combinations. And I know this can be confusing, so I have another table that illustrates this. So the first column is the number of deciles being covered. Here, the case where no entities are covered are, those cases are excluded. So there are only 55 of these. However, when you do it this way, there are 66 of these. So when you put it this way, number of deciles being covered, if we're covering only one decile, it could be the top 10%, it could be the next top 10%, it could be the next after that, the one after that, the one after that, the one after that, and so on until the very last single decile. If we're covering two deciles, then it's from the top 0% to the top 20%, and then from the top 10% to the top 30%, top 20 to top 40, top 30 to top 50, top 40 to top 60, on and on and on and on. So here are 10 different outcomes, different cases, and then 9, and then 8, 7, 6, 5, 4, 3, 2, 1. So that's being covered. Of course, in this case, the ones where it used to be like 0 number of deciles, the cases where 0 number of deciles are being covered are excluded from this. Yeah. So if we are covering 100% of the entire population of the entire world within each generation, then it's from the top 0% to the top 100%, which is the bottom 0%. So there's only one case of that. If it's 90%, then it's from the 0% to the 90th percent, top 90th percent, and then it's from the top 10% to the top 100%, and so on. So you get the point. And I would need to go through all of these per learn rate, and there are 11 learn rates, which are from 0 all the way to 0, and then 0.1 to 0.2, 0.3, 0.4, 0.5, and on and on and on until 1.0. Oops. 1.0. So there are 11 cases. So because I chose to do it this way, where I set the starting decile and the end decile, there were 66 cases, and then I have 11 learn rates. So 66 times 11 is 726. Yeah, so keep this number in mind. And then what I would do is, in this notebook, this is just this is the current version of the notebook that I used to do this. There were some bugs here, so I had to fix them, and I haven't run this notebook after I fixed those bugs. But anyway, this is the current state or version of the notebook that I used. And in this current version, this one that I'm showcasing today in this session, is where I have the entities learn later, but the new ones are added first. See, it's added here first, and then the entities learn. So, yeah, that's what's happening. And did I cover everything? And then when every thing that I said is done, meaning go through all these iterations of learn rate dash candidate ranges, all 726 of them, I would try to have a look at the entity distribution of the final state of the world. I would have a look at their lifespan in all groups, being world, the entities that were struck out, and all entities that were struck out, and all entities that were limited. And then also I would have a look at the slopes of these entities. The slopes and then the ratio of positive slopes amongst all slopes, which is used to determine if an entity has actually improved over its life, over his or her or its life. And yeah, that's basically the gist of it. I use this metric because I realistically cannot go through all the summed utility plots of all entities, whether they be in the world or struck out or limited. So hold on. This is final world 37. Let me just check one thing. Yep. It was okay. That I should look into. But anyway, in today's session, I'm only going to cover the entity distributions because this is a handful on its own. And then in my next upcoming vlog sessions, I'll be covering the lifespans and the average lifespans, age or lifespan, the same thing. And maybe also go on to, not maybe, definitely have a look at the slopes, and then maybe some other things. So when that is done, what happens is this is the code that was used to do this, and well, to do this takes about 4 hours, 5 hours to run all of this. Does it? Yeah, 4 hours and 11 minutes. So let's just say 5 hours on my MacBook Pro. And when I do this, I am left with a plot that looks like this. Now, in this huge plot, or you know, a grid of subplots, are 726 plots, and in each plot you can see what learn rate was used, where the starting decile was, and where the end decile was. So if you look closely, they're all different, and honestly, frankly, this is too much to just look at it. So as a way to skim through everything and share on video, on video a bit more easily, I put together a video of that. So here it is. Each plot will be like 0.2 seconds long, and as we look at this video, have a look at the red dash dotted line as it will move, and also have a look at how the distribution, how the overall distribution will change. Yeah. So here we go. We're still at a point where learn rate is 0. So all these cases that we're seeing right now are where no entities ever actually learned. Now we're at a learn rate of 0.1, which is 10%. Now you see all these red lines just shifting to the right whenever they can. Learn rate of 0.2. 0.3. This video is like 2 minutes long, so it's not that long. Ouch. We're at learn rate 1.0, so every time an entity is chosen to, in quotes, learn, it will just learn everything from a chosen entity from the top 10%. So that was the end of the video. We'll come back to this. So when and then if you look closely at any one of these plots, you'll see that the red line is the average, and then you see in the final state of the entity of the world, the top entity had a sum utility value of 1520 when this was used. When the learn rate was 0.4, so 40% chance of a gene flipping on or off in order to imitate one of the top entities, one of the top 10% entities, and the start decile is 0.1 and decile is 0.3. So 20% of the world being the candidates to learn from the top 10%. So in this case, and the bottom entity was 360, so that's this one right here. This one right here. And the mode, the summed utility value where the most number of entities were was 925. So I think that's somewhere here. This one. And then the population was 1000 towards the in the final state of the world, in the final world, when all the 500 generations had passed. So that's how you look at it. And what I'm trying to look for is, or what we should try to look for is somewhat of a something like this. You have the axis here, and then you would want something like this at the end. This is the absolute maximum, so no entity could actually go past this, because this line is usually the total sum of utility values. So within that problem space, it's not possible to go over this. But if an entity distribution became something like this, is that good or bad? Or if it's something like this, that's too bright, it doesn't really show. Or if it's something like this, or something like this, that actually never happened. Or in a lot of the cases, a bimodal distribution. Is that what you call it? I think that's what you call it, right? A bimodal. So something like this. Something like this, as opposed to something like this. So what am I looking for? Well, ideally I want something, ideally I would like something like this. A nice bell-shaped curve, but kind of steep. Or something like that, anything like this, but towards the very end, towards the right end, so that give me a good color, the average is high, well, higher than if anything was here, but the population, the what do you call it? What's that word for population? Population. I forgot. Let me just Google it. Sorry. I forgot. Oh god. Oh yeah, demographics. Where the where certain metrics like the average, the standard deviation, or anything make it look like this. These two. And we have the entire population, or something close to the entire population, which is 1000. And we have a very robust or stable shape. Because you'll see very soon that, because you might think that an entity distribution that looks something like this is good, but I don't think that's good. You'll see why. For instance, if we for one of the extreme cases, if we had the learn rate at 1.0, 100%, and then we had all the entities learn something like this. All the entities learn. So the start decile is 0, end decile is 1. And what happens at the end, or well, at the end and in the final state of the world, is that we only have 277 entities left. So the other only 27.7% of the entities survived. But this is after generation 500. So this is one of the many generations after the population has peaked and plateaued. So let me illustrate that. If this was a summed utility plot, how it usually goes is this is generations, and how it usually goes is it would go up and then it would peak and then plateau at around 100, or before 100, before generation 100. So, and because we're doing it until generation 500, once it reaches this plateau, and because there weren't any visible dips so far, not that I know of. There could be if I dig deeper into it, but so far let's just suppose that there were no dips. So when after this plateau has actually formed and keeps continuing, it continues on. This continues on. What happened here will happen here as well, and happen here as well. In every one of these generations after the plateau point will happen. So you can just safely assume that if in the final state of the world we have only 277 entities survive, and the rest 723, is that right? 723 entities are somehow not ended up in the population and cannot move on to the next generation. I don't think that's wise. I don't think that's good. That's not good news, because it means that you're dying. You don't have a stable population. You always have to keep making or introducing new entities through procreation in this case. So that's not good. That's not healthy. So that's what happens when you have an entity distribution that looks like this. It means that a lot of the entities just got struck out. Most likely they got struck out because they scored so high, which means that they're very, very close to the max constraint threshold, and just one tiny bit of mutation, one gene mutating, will just cause them to go over the threshold and get struck out. And of course, in this case, you won't be limited out of the population, because so many entities are struck out, and the population is below the maximum population threshold. So ideally, what that left me to conclude, what that left me to conclude, is that too high of a learn rate isn't that great, and if you set the the candidate range something like 0.1 to 0.5, so that's something like where is it? Zero 0.1 to 0.5, 0.1 to 0.5. So something like this. It means that we are leaving all the entities that be in here. We're just depriving them of the opportunity to learn. And something like yeah, let's have a look at when we only had this from 0.0 to 0.4. 0.0 to 0.4. There we go. So what that leaves us is that because the entities that were here in this red shade, should I make it red? Make it green. No. Red? Okay. In this red shade, the entities, if this is the entire world in one generation, the ones that would be in the red cells, meaning the bottom 1, 2, 3, 4, 5, 6, the bottom 60% do not get to learn. And what that does to the population, and what that does to the population, which can be shown in the entity distribution, is this. It actually gives us, well, what's this called again? I forgot. Yeah, it is called a bimodal distribution. Yeah, so I was right. So it gives us a bimodal distribution because these entities didn't learn, but they're still in the same world within each generation, and they procreate. But what happens is that when the procreate function is set to favoring highs, the entities who are at around the top are more likely to procreate. But since only these entities got to procreate, the gap between these two groups will get wider, and this is what happens. And the gap just keeps getting bigger if the learn rate goes and gets higher. For example, let's have a look at when only 30% of the entities were chosen as candidates. For example, from that to this, so that's 0.3 to 0.6, 0.3 to 0.6, I hope my computer doesn't crash. And then let's look at learn rate of 0.7. So again, bimodal. 0.6 learn rate, 0.6 bimodal, bimodal, bimodal. So this again happens because we're leaving these two groups. You know, we don't give them enough. We don't give them any opportunities to learn. But then again, these top 30% or 20% in this case, these top 20% are kind of okay because they were high to begin with, so they would just procreate, and well, some of them could actually slack and start slacking and just end up going down in rank in the some utility rank order, but still, but these things, entities in these in this section, in this range, don't get to learn. So that's what happens when you get this, and that's what happens when, well, let me rephrase that. This is what you get when you do, this is what you get when you do this, when you don't give the bottom entities, the very bottom entities, or some of the bottom entities to, to some of the bottom entities. When you don't give a certain number or a certain percentage of bottom entities the opportunities to learn, you get a bimodal distribution. And even when the top entities are included, so for example the top 40% were included, yeah, still bimodal. And so what you do want to do is make sure that some or all of the bottom entities, or make sure that a majority or all of the bottom entities are included. So it would be something like the bottom 40% or the bottom 30%. So the starting decile would be something like 0.6, and the end decile would be 1. So 6 to 1, 0.6 to 1. There we go, 0.6 to 1, learn rate 0.5, let's say, and this is what you get. But in this case, the population is only 740, so only 74%. It's 74% because it's 740 out of 1000, so only 74% survived. Okay. Whereas in this case, where the starting decile was 0.6 and the end decile was 0.9, this weird thing happened. It's not exactly bimodal, or kind of, because you could say that this is also a hump, but yeah, this looks a lot like this, and we only lost 2 entities. So like for instance, when the learn rate was 0.5 and the start decile was 0.6 and the end decile was 1.0, the population was 740. However, with a learn rate of 0.4, we still have the population at 1000. Yeah, so we kept all the entities. In this case, the top entity was 1505, but however, we know, or rather I know from my previous experiments and simulations, that that 1540 is the best of the best, the best possible summed utility score. So in this case, you could say that this generation, after generation 500 or during generation 500, things got really unlucky and the top entity had to be struck out, or it was limited for some reason. It was either one of the both, because I just remembered that I also shuffle the world before I do this, before I limit the population. Yeah, which was a measure that I took in order to increase the lifespans of limited entities, or entities that would eventually be limited, that were likely to be limited. So by shuffling it, I could just guarantee that they have a higher chance of moving on to the next generation. So, for example, this one looks very promising. Learn rate 0.3, start decile 0.6, and end decile 1.0. The average is 1283. You'll see that as the learn rate goes up, the average also goes up, which is kind of obvious if you think about it. Then again, if the learn rate is too high, we start losing the entities and the population size gets smaller and smaller. So that's not nice. Let's have a look at when it was only the bottom 30%. Bottom 30%, and then so bottom 30% as opposed to the bottom 40%. Yep. So the average was this. Let me just screenshot this. And then also let me just screenshot these two. There we go. So learn rate 0.4, start, this is, let's have a look, this is the bottom 40%, bottom 40%, this is the bottom 30%, bottom 30%, and learn rate, so I should compare these two, and of course the average is lower by about 22. The top, well, as I said, this was a bit of an unluck there, misfortune there. The bottom, yeah, kind of mode still. So a bigger range, a wider range of candidacy does increase the chances, or it does increase the metrics does raise the metrics. So what if the learn rate was 0.4 but everyone got to learn? Let's have a look at that. So 0.4 and everyone got to learn. It's going to take ages to do that. Almost there. So there we go. So 0.4 and everyone got to learn. You see that the average compared to somewhere around 1300 is definitely lower than an average of 1408. But the population is only at 456, so around 54% of the population dies per generation. So that's not good. So you don't want this, which means that you have to limit the candidate range, or you kind of have to focus the candidate range towards the bottom half, or somewhere around the bottom half. So let's have a look at learn rate 0.4 and the bottom half there. Let me screenshot this. This is the bottom 50%. %. But we still do have an issue here, because only 86 of the population survived. I don't like that. No, I don't. Because it's the order in which it works is that I apply the selector first, and then I shuffle the world, and then I limit the population. So when something like this happens, so for example 860 entities, or something like 418 entities, it means that during this phase, when the selector function was applied, 582 entities were struck out. So the population limit, the population limits, the pop limit function doesn't have to do its job, doesn't do its work, because there is not enough entities in the world for the pop limit function to act upon. So that's not good. But when you have something like whenever you have the population set to 1000, where is it? Something like this, for example. When you have this, it means that even after the selector had done its work, there was still more entities in the world than 1000 entities for the pop limit function to work, to do its job, and then limit the population to 1000. With or without shuffling, it doesn't matter. This shuffle doesn't matter here, but you get the point. So if the population in the final state of the world, or if the population in the plots here is lower than 1000, it means that we kind of overlearned. It means that we kind of let the entities overlearn, whether it be on an individual basis or a collective basis. And the same can be said if, for example, if we had like a learn rate of 1.0 and apply the candidate range to the bottom 40%, that also happens. The same thing also happens. The bottom 30%, again, same thing happens. So it would be wise to set the LR, the learn rate, to somewhere between, at the minimum 20% and maximum 40%, and the candidate range CR to bottom 30% or 40%. Yeah. So for instance, if the learn rate is 30% and it was applied to the bottom 30%, which would be 0.7 to 1.0. So let's go have a look at that again. Or is it here? Yeah, it's here. It's this one. Granted, we do have somewhat of a lower average, but we have an entity distribution that kind of looks robust. I know it's not exactly a standard normal distribution, but it still looks robust. So I'd say this is good. Or 40%. This is also good. So before I leave, I'll just try going over this video again, see if I spot anything unusual, something more, and then I'll end the video on that note. Playing it for the second time. Okay. Nothing else unusual. Okay, thanks for watching. I'll come back with more stuff after I analyze the results and spot and fix any other potential bugs and issues. So thanks for watching. Bye. Wow, this video is an hour long. Damn.